very relevant for us very relevant for us when the robot is this small and you want some sort of good endurance out of it. So let's see, what's changing. Okay, yeah. So we introduced tiny robot learning, and we deployed tiny machine learning model on board a super constrained nanocopter. And it's kind of hard to get a sense for how tiny these things are from a slide. It's really can fit in the palm of your hand. It's about 30 grams. I don't know what it is in American units, but it's really light. We use deep reinforcement learning for onboard navigation. So we train a policy and we do inference on board of a really constrained tiny robot. So yeah. So what is source seeking? Source seeking is the robot will seek a source. It could be light, gas, or radiation sources, and it's generally perceived as an important task in search and rescue or inspection. So one of the things could be a burst gas pipe, and instead of looking for it everywhere, you would want to do some sort of more informed search based on a gas sensor. In this project, we focus on light seeking because it is ever so slightly less challenging. And it's also easier to debug because we can actually see where there's light, whereas for gas, that would be a lot harder. So yeah, we really imagine small, agile, inexpensive aerial robots to do this because it would be potentially more scalable if it's cheaper. You know, those really large flying drone systems can cost upwards of $20,000, even much more actually. So yeah, we use LightSync as an application to show that a very small deep reinforcement learning policy can solve this problem effectively. The method that I'll go over is in the areas of system design, the simulation environment we've used, and the partially observable mark of decision process. So basically the reinforcement learning setup, and then how we did influence on the drone. So this picture I think is kind of funny because if you think about consumer drones, the red drone is basically what you would expect, like a DJI drone, and the tiny drone is really tiny. So yeah, here we stress that aspect a bit more. So on the compute side, we have an ARM Cortex chip, which is not just used in drones, but in many MCU tiny ML applications. It has one core at 168 megahertz, but maybe more importantly, the constraint that we were annoyed or challenged by the most was the RAM is just less than 200 kilobytes. And you have to imagine there's also other things to run on a system like this. So there's a number of flight stack and some other things that we have to store. So really the RAM we had left was 33 kilobytes. And we want to store almost everything in RAM because that's way faster than storing the weights of the network in flash. So this was certainly a design constraint. The sensors we had on the drone is an optic flow deck, which is, yeah, we can go into this deeper in the Q&A, but it's basically the text optic flow. So how fast are pixels moving and in what direction. You can use this to control the drone, so to just give it some sort of velocity. Laser rangers to avoid obstacles, and a light sensor that we use for seeking the light. Now the simulation environment, and this is some of the great work by Sri, also from the Harvard group. He's still at Harvard, and it's an Unreal Engine environment that can randomize an environment with different obstacles and different parameters, and it's really easy to plug in your application and learn a policy for whatever you're trying to do. So in our case, we added a source. We modeled the source using the Gaussian distribution. So we went into the testing area and we measured light intensity and fitted a curve to it with respect to distance. So we could model the light source into the simulation environment. So this is about as far as I'll go on the DeepRL setup. So we use the DQN, DeepQ learning, but this is kind of the input. So we have a neural network, and it takes in the laser rangers. Laser rangers are pointing in 4 directions, so that's why you see those four lasers on the left side of the slide, and then two light sensors, and that is those are custom features that we designed that give some sort of information over time. So it's a low-pass version and a raw version of the light source, more or less, because these sensors are very noisy. What happens is it goes in, and the drone decides to move forward, right, or left. And based on that, we will navigate towards the source. So that behavior is always learned in simulation. Now, the inference implementation, we have considered more common approaches, and keep in mind this was in 2019, so the implementations might be better now. But we found that TensorFlow Lite wasn't really fast enough, so we only had a couple hertz. And with UTensor, we were fast, but there was a known bug where at the time there was a really small memory leak. But if you have a memory leak of a kilobyte every cycle, and you only have 33 kilobytes, then you get really short experiments. So we ended up coding our own lightweight C inference library, and because the network we were using was basically just fully connected layers and some simple nonlinear operators, it turned out really well. So yeah, we could run it basically at 100 hertz faster than the pooling rate of the sensors. Then we compared with some baselines in simulation. So yeah, in robotics typically, and I guess also in many more fields in science, you'd have to show how your method performs compared to some other methods. And in this case, the two other methods we compared to is one, just randomly picking between the three actions that I just mentioned. So that's forward, right, or left. The other one is a finite state machine, which is basically a very big if then else structure, which we designed for this purpose. And we compared them in simulation. So you see here that deep reinforcement learning achieves the best success rate. And then you also see that the number of steps is quite competitive. One thing to note is that you might think, oh, random actions has fewer steps for reaching the goal than ours. But the reality of this is that random actions only finds a source in 30% of the time. And when it finds it only finds it when it accidentally was very close. So yeah, that's something to keep in mind. And then we did flight tests in an actual physical environment with the drone. And again, our success rate was better than the finite state machine. And we tried a bunch of different obstacle densities. So drone has to dodge obstacles and walls before it can find the source. And we saw different performance. And most notably, we saw that deep reinforcement learning is sort of scales better to unseen scenarios compared to a finite state machine baseline. So, we only really tested in simulation on some low obstacles and even no obstacles. But in the real world, it even does pretty well on high obstacles, which is really like you're moving through a forest of obstacles is kind of what's happening. So yeah, here we got a demo. So you see this really tiny blue dot is moving towards the source. It's kind of hard to show things in demos, but that's kind of what I can show right now. And then here's some information on this project. We're not done with the stuff yet, but this is kind of the end of this first part of the presentation. So yeah, mostly came from the Harvard Edge Computing Lab, papers in archive, and the code's actually also on GitHub. Now, so after we worked on this, the idea was to extend it towards a slightly more challenging application and to explore some new algorithms. So yeah, so we call this gas source localization, GSL, and yeah, basically as the name implies, it's using robots to find the gas source. So it's very similar to the light seeking that I described before, but now we're looking for a gas source, and ideally we would be using a swarm of drones instead of just a single drone, because it's bigger area and it might be a little hard with one drone. So in this work we contribute a swarm, a fully autonomous and collaborative gas-seeking nanocopters. They're just as tiny as the previous work. A novel bug algorithm for gas source localization using extremely little resources and evolved parameters, where a bug algorithm is an insect-inspired algorithm of a finite state machine. So again, pretty much just a big if-then-else kind of graph structure with transition models. And then a pipeline for autonomous gas dispersion model. So this is kind of important for doing the evolution part of the parameters. When we started this work, kind of an interesting existing body of work. So this is one example of it where a drone is using wind information to find the gas leak. And if you think about it, it's actually a really good prior leverage, because the wind and flying upwind, in all likelihood you will be able to find the gas source much easier. So that's something they're doing. But one of the limitations is it only works in really tiny environments. So this particular instance, we have an arena size of 0.8 by 2 meters, like 6 feet by 2.5 feet. So it's really tiny, and we wanted to see if we can find something that works on really large obstacles and in more challenging environments. So we go again over system simulation and algorithm design. With the system design here, we use the same platform. There's something called the BitCraze Crazy Fly, which is an entire company dedicated to building these research-oriented drones. And for a couple $100, you can buy one. But we added an optic flow deck again. We added laser rangers. This time we also have our custom PCB, of which the design is online, so it's open hardware. And it has a gas sensor and it has ultra wideband. We use optic flow again for control. We use laser rangers for obstacle avoidance. We use the gas sensor to sense gas. And ultra wideband is a very powerful signal in order to get relative positions for the other agents in the swarm. So it's basically a beacon with some intensity. So you get like a radius without bearing to one of the other agents. And if you feed this into an EPF, into a common filter, you can discover the exact relative position of the other agents. So essentially what this drone can do is it can, without any external structure, determine the relative position of the other drones in the swarm. And the simulation pipeline first has a step which we call auto GDM, auto gas dispersion modeling. And then we go into Swarmulator. So this is like a really lightweight 2D simulation environment for finding a suitable policy. First, auto GDM. So we have this pipeline where we do computational fluid dynamics, and this is often used for things like the designing things that interact with either air or some other viscous substance like water. So we first do environment generation. So we generate an environment where the agents will be tested in. Then we feed that into a CFD pipeline, which has a mesh. So it basically is a computational solver. It's a flow field, and then disperse particles of gas into this 3D vector field of wind. Okay. Then on the algorithm side, we use SniffyBot. So the name of this is kind of, we thought it's a sniffing algorithm. So it's a sniffing bug algorithm, because the algorithm we use is a bug algorithm. So it's an insect-inspired finite state machine. One thing that I wanted to go over is sort of that we use particle swarm optimization at the base of it. So particle swarm optimization is really a search heuristic that's used not just in robotics, but in design optimization and other search techniques. And in this specific plot, what you see is that these sort of nodes or particles, they do their own little optimization, but they also communicate each other's findings. So they're trying to find a global optimum here, and or minimum, I guess, and they do that by communicating their state without likely converging to local optimal. And then we also do evolutionary optimization of the parameters. So as I mentioned, these finite state machines are typically like very convoluted if-then-else structures, really a graph with complicated transition functions, and our algorithm is no exception. So to tackle sort of the engineering aspect of this, or the optimality aspect of this, we decided to evolve the parameters of the algorithm. So there's 13 parameters, and part of it is waypoint generation. So how do you weigh someone else's experience versus your own experience? And this comes back to particle swarm optimization. So if I smell a lot of gas, like how much confidence do I sort of attribute to that? But then there's also the obstacle avoidance and swarm avoidance, because really the system needs to get a lot of things right. So it needs to be able to pass through small passages with multiple drones at the same time. It needs to avoid walls, objects, get to the gas source, and collaborate effectively. And all these things are really helped by optimizing the parameters of the algorithm. So you add a cost for each agent, which is in simulation, which is kind of the average distance to source, and then the penalty for collisions, of course. Then what I find is a really interesting problem in kind of in machine learning in general is you have the hard instance problem. So let's say there's some distribution, and I like to use the analogy of learning a language, and there's some words that are really hard. If you optimize an objective, optimize a policy for getting the entire distribution right, then it might just converge to getting the easiest instances right. So in this case, what happens is the left environment is super easy to find the gas source. It's kind of being dispersed in a very somewhat more trivial way. So we just call this dispersion. Whereas here we have local optima, really complex obstacles. This is actually a really tricky obstacle to avoid. And yeah, this is what we call the hard instance problem. And a solution that we and some other scientists in the past have come up with is what's called doping. And this has nothing to do with athletes or cycling, but what it has to do with is to focus more on the hardest words. So let's say that you're studying for a test of French, then the odds of you focusing on the harder words that you don't know yet should be higher. And in evolutionary optimization, this is kind of, we present the optimizer with more and more of the harder instances over time. So we record sort of the performance, and if it does really well on some class of objects and or of scenes, then we transition more towards the harder instances. And here are some of the results. So we first evaluate everything in simulation. And, we evaluate in success rate, average distance to source in the run, and an average time to source. So when does it find the source? And we outperform the manual parameters and the manual parameters without doping in all parameters. So that's good news. And one thing that I think is kind of interesting here is that if you plot the time or the average distance to source, what you see here is if you don't use doping, then this tail gets really long compared to using doping. So that means that these hard instances are really giving us a rough time. This is what I conclude from it. And then this is a much more visual representation of what's happening. So manual parameters means this is what we sort of in physical experiments found to be pretty good. And then with evolved and doping, you get much more direct trajectories. And something that I find interesting is, like we made it kind of more risk averse, which is why this is taking so long. Like they cannot sneak into this corridor all at the same time. But the optimization found that it's actually better to get to the source quicker and fly for less long, because that's actually safer. And I think that's a super interesting result. So this is what it looks like in simulation. I hope Zoom is, it's visible over Zoom. But all these little circles are agents, and those green lines is lasers that we are modeling. So yeah, that's what it looks like in simulation. And then we go into physical experiments. So yeah, this might be really hard to see. But all these kind of really tiny blue dots is what the drones are. And in this case, they already flew back, but so the source is here. So the tiny table every time is where the gas source is being dispersed with a small fan. And the task is, of course, for them to find that gas source. In this case, one of the drones has lost its battery. So the battery lasts about 10 minutes. But yeah, if you run repetitive experiments towards the source, then sometimes those batteries get bad. Yeah, this is a final experiment where we just didn't put any obstacles, and you can tell that this form is just sort of creeping towards the source and stays there. So in conclusion, we have, like in this work, we contributed the first fully autonomous swarm of fast-sleeping quadcopters in cloud and GPS environments. The paper is online in arXiv, and we have a GitHub repository with all the firmware simulations and everything. It should make it possible to replicate all of our experiments. But yeah, please reach out if you have questions for like after the Q&A. We used to have questions for like help implementing something similar. Before ending this talk, I would like to thank all the collaborators. So yeah, on these specific 2 projects, these are the co-authors that have made this possible at Harvard, TU Delft, University of Barcelona, and Sandra at Google Play. So yeah, thank you very much. That was it for me.
Super, great. A round of applause from all the participants, and that was great.
Art, there's a bunch of questions in the chat.
Yeah.
I was starting to try to answer some of them as we went through. So I sent you a message with like the ones that I didn't totally answer, but I can also just like field them at you if you want. Whatever is easy for you.
Yeah. So
okay.
See if I go to, so you sent me a message on
I sent a message on Slack,
Zoom.
In case that's helpful. If that's not helpful, I can just start reading at you. The first one was just how long does the battery last on the drone?
Oh, am I back? I think
Yep,
it
you're back.
froze.
Oh yeah,
okay,
no, the first question was just how long does the battery last on the drone?
Yeah, so it lasts, in theory, it lasts about 7 minutes with the payload that we added. But something that's kind of useful to know is that, you know, if you sink more money into this, then you can definitely get better endurance out of it. So there is versions of this that are professional for companies and surveillance purposes. They last like a full 20 to 30 minutes. But they cost $100 per drone. And we spend like $300 per drone. So yeah.
Is like sort of associated with that, there was a question around how much weight the robot can support. So is there sort of just is there a trade-off here between payload and battery life?
Yeah, for sure. And actually, the battery life in the second work that I showed in this work was a lot worse because we loaded it up with so many sensors. So the trade-off is really sharp actually, because this gets dangerously close to the maximum weight. Like at 40 grams, it basically cannot take off anymore. So it means that the propellers are just spinning really close to its maximum at this point. Yeah, great question.
Do you think, I guess, even the professional one, like 20 to 30 minutes is not great battery life if you actually want to, you know, explore a large area per se. Is the challenge mostly on the battery side or like the mechanical side? Do you think there's software things we can do to make it fly farther?
Yeah, that's also a great question. So yeah, first on the hardware side, I think there's you know, people have thought about better propeller designs for a while, and I'm not quite sure if like motors or propellers can get much better than what they get when you spend $100 on the system. What you can do though is you know, just fundamentally the design of a quadcopter is kind of limited. So if you would make it a fixed wing, it can sort of glide much better, and the endurance should get much better. And also you know, if you make it a tiny bit larger, if you look at some of the DJI systems, they're still very cost effective. I think you can get to a very good endurance. So you would just make it like, you know, it'd be 100 grams or 200 grams. And I think you can get to a very useful endurance, but yeah, full trade-off. Like if you get it this low, like I think the RoboBee can do like 20 seconds, right? So, or something like this. Depending on what configuration, and this can do a little bit longer, but yeah.
Yeah, no, that makes sense. And by the way, because I think a couple people are asking, this is the Crazy Flight, right? Drone.
Yes, yeah. Excuse me, I think I didn't mention it correctly, but yeah, let's see.
And there's that. I think that company keeps releasing a new version every couple of months, but they exist.
yeah, the company is called Bitcraze, and it's kind of incredible how they're basically banking on the research community to maintain their company. It's kind of incredible. It all works out. So I think I saw a couple of questions while I was talking about the inference library.
Yeah.
It is not open source, but I think that the firmware of the drone is open source, so you could find the implementation. But what we did was like really simple. It's basically just a for loop to do a message notification. So yeah, it's like I remember kind of like being so frustrated with all these custom libraries, and I was like, okay, this morning I'm gonna try just code up a for loop, and somehow it worked. So yeah, it's not super sophisticated. Let's see. Yeah, I can keep going through the questions in the chat if that's
Sure. Yeah, that's great.
if that's useful. If that's useful. Can you please highlight how insects use navigation technology to find location and destination, and how have you related those information on the inference library? So there's definitely still discussion on how insects actually do navigation and how much memory they have and so on. But there's some behavior that has been seen in some insects is that they do this thing called wall following. So instead of making a map of the environment in 3D and solving it with a solver like ASTAR or RRT, what they might do is follow a wall until they can get into a room or something. So that is something that we've also used. This can be used in outdoor applications. Yeah, that's a great question. I think it's kind of a separate problem, but in the current configuration, if you would place it outside, it would definitely blow away. But there's work on sort of more the control side of things to improve that, like and state estimation, I guess. So in the current configuration, I wouldn't place it outside, but we think it could be used outside if things are better. So so again, the drone that's much more expensive for yeah, actual industrial applications, they can fly outside, even though they're roughly the same size. The system slide, I think, yeah, I'm not sure. I think I was probably in the Snippy bug slide. So while I'm currently sharing the slide, let me know if there's any specific questions. What is your ML models? What is your drone break rate? Are you breaking one? Yeah. Yeah. So I think for the Sniffy bug, this swarming example, like the swarming paper, we broke a lot of drones. So do you have any more comments about this, Jeremy? I think you asked this question, right?
Yeah, I do the robot cars and I break Arduinos daily. Yeah, I was just kind of wondering, I get that you swap parts and you keep things going as best you can, but yeah, the drones, when testing your model, to begin with, it must have been a little frustrating. Are you feeling that things are getting better?
Yes, one of the nicer things about these drones is that the parts that break most frequently can be replaced. So there's these lags, and if a crash, they kind of absorb the impact. So these are like the plastic lags, and then there's propellers break very often. The motors sort of have a life cycle that's very short. So from the outer part of the drone, we almost see as consumables. And then there's things that can happen in the inside of the drone. I think batteries kind of have a limited cycle as well. Yeah, I think it's good enough for research, but definitely, like as you said, you burn through a lot of drones. Like if you take good care of them, you can maintain them for longer. But there's certain parts that just don't last as long.
So to do work like yours, where you typically have about 4 or 5 going at one time, a starting point of 10 would be your bare minimum. And then lots of extra parts.
Yeah, I'm not sure if so yeah, if you have the entire drone, then you also have the PCB and stuff, right? Like, and those things typically don't really break as much. So I'm not quite sure how much, but we definitely used like enough, like of the outer parts similar to a swarm of 10 drones. Yeah. So you definitely need like 2 or 3x to do exhaustive set of experiments, because we also did like a bunch of experiments. We didn't just test it once, but very exhaustively. We did something like 30 or 40 flights for the final algorithm, and before then, there's of course like testing and so on. So yeah, does that make sense?
Yep.
Awesome. Yeah, thanks. That's a super cool question.
Are there other questions? I don't see hands up. Oh, there we go.
Yeah, I also see one more question in the chat. By evolutionary optimization, doping, do you mean the use of genetic algorithms? Yeah, so evolutionary optimization would mean genetic algorithms. Then doping is kind of something we add to that. So there's a stronger focus on the, like during the evaluation, we slightly start focusing more and more on the harder cases. So that's what we mean with doping.
And I think Andrew has his hand up to ask a question as well.
Oh.
Yeah, this is really, really awesome. And I have a question. When you're doing the experiments, I guess, so like in an insect, right? They're kind of awake all the time. And so, they can like find the light whenever they're sort of like awake and doing things. So how does it work in your experiments when you like go and set out these drones to do them? Do you have to like manually turn them on every single time, or do you just kind of like have a room and you flip a light here and there and it's like, oh, okay, let's check out what they do today, kind of thing?
Yeah, that's a great question. It's actually like, I must admit, testing these systems exhaustively is kind of painful because there's a little battery in here. And so yeah, to do a test, you have to plug them on, make sure they're all connected with their telemetry. So yeah, it's definitely not in the same way as insects, I guess. But yeah, that's definitely like a systems challenge that might be very interesting to tackle later on. Okay.
Bart.
Yes.
Most of us are from sort of an Edge Impulse or maybe TF Lite background. It sounds like you're doing everything on your own. Are you using some sort of TensorFlow or some kind of machine learning framework? Can you comment on that?
Yes. Yeah, of course. So especially during training, we use things like stable baselines, which used to run on TensorFlow. But right now we've sort of transitioned to, or like I think the latest versions of stable baselines has a core of PyTorch. And I think there a lot of people that I've worked with are sort of transitioning more to PyTorch now. For edge devices, some of the recent work I've done after this is more on something like the NVIDIA Xavier, right? So that kind of has a little bit more power. But they also have sort of custom inference libraries for that work pretty well. But yeah, I think this case was just like we really wanted, like we really tried really hard to use something like TensorFlow Lite, even though like it's kind of a beta release at the time, I think, in 2019. But yeah, this use case is so extremely limited. It had 33 kilobytes of RAM. It's just really hard to get any library to run in a good way.
Right.
Let's see, is there any more questions?
Marco.
I think there's no more questions. So thanks a lot, Bart. Again, that was a great talk. I hope you can join our Discord channel. So if people have more questions, then they can ask there. Super, excellent. Matthew.
Thank you so much for the invite.
Oh, thanks for presenting. That's great.